Good afternoon, everybody. My name is Vishal Ramnath, and today I will do a presentation entitled Application of Computer Algebra Systems for Technology-Enhanced Automated Engineering Assessments. This is the abstract, which I will not read in detail. Essentially, the objective is to illustrate how to implement a computer algebra system in an automated assessment. And the novelties will be illustrating how to use Taylor series to simplify the calculations at the end of the day. So it won't be very theoretical, it'll be more hands-on, and it'll be using examples to illustrate the underlying concepts. So at Unisa, I work at the School of Engineering in the Department of Mechanical, Bioresources, and Biomedical Engineering. Traditionally, there were three options to use automated assessments after the phasing out of Samigo with the new software called Moodle. The first choice is obviously simple multiple choice questions with static variables. Second choice is to use calculated questions using random variables. And the third choice is to, in a certain sense, use calculated questions but incorporate it into multiple choice. In Moodle, this is known as randomized multiple choice or computational multiple choice questions. So a typical problem in engineering, you have a schematic of some sort, and the student in an assessment, like a quiz or a test or an exam, must attempt to evaluate and solve the underlying problem. This particular problem is just a simple beam in horizontal orientation that is rotating with a mass that is exerting a downwards force, and as the beam rotates, a spring force counteracts the motion. And then there's an oscillatory motion, and it has simple harmonic motion. The particular details is not terribly important, it's just used as an example for the system. So historically, you would utilize Moodle, and you type up the question in a text box using wildcards with curly brackets, some latex, and you would have certain values in the question that you would evaluate. And after you type in the question and populate it in a question bank, you would then type in a formula for the answer. And the curly brackets are wildcards or random variables. And in the Moodle system, you would have a range of values. And when the student undertakes the test, he or she would have a unique random value. And they would have to type in the correct answer to a certain amount of decimal places with a certain tolerance. And you can incorporate this methodology also in multiple choice questions. So this is an example of how a question would typically look. There would be a story with some random numbers, and the student would have to work out the most appropriate answer, A, B, C, D, or E. Every student would have a unique answer where every single student, whether it's 50 students or 500 students, will have different random values. So every student will have different answers, and there would be different values in the options of the multiple choice. And of course, the multiple choice will be shuffled as well. So it would be essentially impossible to cheat at the end of the day. Moving on. The same question, in other words, the same story, could be used, and then you would ask different things. In this case, question 1 would be to work out omega n, the natural angular frequency. Copy and paste the same question, and question 2 would be to work out a parameter a and b in some formula. So in this particular quiz, there were 5 questions that were recycled. This is the process to solve the problem. There would be some diagram or an explanation of a diagram. You would then work out some hand calculations, and you'd end up with some formula. And then you'd post-process the formula to work out the answer. So, referring to the methodology, a practical problem arises that in this problem there may be very many random variables, m, l, t to 0 dot, omega n, t. In this problem there are about 7 variables. The problem is that in general these expressions will become very long and very unwieldy, and it would be very difficult to type answers in the Moodle assessment shell. At the present time of this presentation, there is no simple way to convert MATLAB or Python or C++ expressions into the syntax for Moodle. Moodle has a Pascal type of syntax, and although you may calculate arbitrary expressions, you have to manually translate it into a format that can be amendable to a Moodle assessment. Moodle is based on XML, Extended Markup Language, so there is no possibility to incorporate procedural routines like for loops and if loops inside the Moodle. Moodle is basically a website, an HTML website. So that's the challenge. Very lengthy expressions, no easy way to convert it, no easy way to program. How do you solve the problem? That's the purpose of this talk. So my initial investigation was to use a computer algebra system and convert the long answers into equivalent Fortran expressions, and from Fortran, which is a simpler language, to convert it into the Moodle syntax using a particular criteria, for example, powers and exponents and so on. The challenge with this is that the answers may be many lines long and may be literally half a page of formulas. How do you manually type half a page of formulas into a Moodle shell without running into errors? The answer is with difficulty. So the purpose of this talk is to incorporate how to use Taylor series to solve and simplify the expressions. We recall from our mathematics that any multivariable function can be approximated to first order in terms of partial derivatives, or to approximate to second order with a Hessian matrix and a gradient vector. This is standard calculus in first and second year. So the challenge is we have some arbitrary complicated expression which may be very long, many inputs, many lines of code, and to convert it manually would be very challenging. The challenge is it would be tedious, very time consuming. It would be error prone because of the length of the expressions. There would be numerical issues in Moodle when Moodle tries to evaluate numerically arbitrary and very long expressions that could be page, 2 pages of formula. And there's no simple way to manually convert into an expression. So these are the challenges. How do we solve the challenges? The challenge I identified could be solved using computer algebra systems. If we have analytical formula for the expressions, we can construct a Taylor series expansion instead of a Maclaurin series, and then the Taylor series would be a simplification of the formula. So we have a long, complicated expression. We convert the expressions with arbitrary terms, Roman letters, Greek letters, into parameters x1, x2, x3, and so on. And then we form a simplified Taylor series approximation of the arbitrary expression, and we truncate it. So it's literally this long, complicated expression is some constant plus the variable minus a constant times another constant plus and so on right to the end. So x1, x2, x3 are your variables corresponding to the mass, a length, an angular rotation speed, a natural angular frequency, and so on and so forth. So that is the mathematical formula at the end of the day. When you utilize the Taylor series expansion to convert it into a simplified expression, you literally have to work out an addition plus a multiplication of these terms. X1 is a random variable in a range from a minimum to maximum. A1 is a constant. G1 is evaluated as a partial derivative. And that's the expression at the end of the day. So you have the formula for the expression or the answer. You work out a reference value, and you basically approximate this complicated expression as a polynomial expression, or if necessary, as a quadratic expression. And at the end of the day, to implement it in a computer language like Python, to work out all these complicated partial derivatives, in Python, you would literally have computer code which is about 30 lines of code. So this is what Python looks like. It's an open source free computer algebra system that can do numerical calculations and symbolic calculations. And you type your computer code in a window. You can have another window to look at the expressions, and you can also work out the numerical values. At the end of the day, you just want to work out the partial derivatives using the computer algebra system, and then when you implement it, you would work out the partial derivatives and just multiply it. This is what the picture looks like in Python, and this is the computer code. You import the symbolic algebra, you declare the random variables as in symbolic terms, you type in or construct the expression for the answer, you work out the partial derivatives, you put in a point about which you want to approximate, you convert it into an equivalent numerical function, and then you work out the answers to the numerical function. So at Unisa, we have different colleges and different schools, and different people use different types of software. I work in mechanical engineering, and I prefer to use Python, which looks like this. But for other colleagues, it may be easier to use a software such as MATLAB, which may be a little bit easier to implement. So although MATLAB is mainly numerically orientated, it can also be used for symbolic calculations as well. To implement the same problem in MATLAB takes about 20 lines. Well, about 30 lines if you work out everything. So it's literally 20 or 30 lines of computer code for the problem that has been presented in this presentation. So this is what the computer code looks like under the hood. You import the symbolic library, you construct the function, you work out the partial derivatives, you convert the symbolic formula to numerical formula, and then you evaluate the expressions at the end of the day. And that's basically all there is to it at the end of the day. So the presentation I have communicated has been orientated mainly on the numerical side because I work in mechanical engineering, but it can also be used for symbolic expressions. We've had an expression for a function. Typically, a student might make an error in 2 or 3 terms. They work out a force or velocity incorrectly. We can put some error terms into the expression. And then once we incorporate the errors, we can also work out a symbolic Taylor series expansion and then compare possible or plausible student answers at the end of the day. And that's the way to generalize the method over there. And this is basically the end of the presentation. So to summarize, I have developed a method that makes it possible to implement arbitrary, complicated engineering problems with many variables as a simplified mathematical model. The model can be implemented in common, widely known computer algebra software such as Python or MATLAB or GNU Octave or Maxima, which is based on Lisp. And the underlying method that I've developed can be conveniently used to automate engineering assessments with hundreds of students using randomized data for arbitrary expressions. And that is essentially the underlying rationale for the research that I performed. And I will now take any questions and clarify any issues that may have been identified by the audience. Thank you very much for your time, and that is the end of my presentation. Keep well. Bye-bye.